Okay, so like in the last example, let's look at this one. This is the one we want to determine whether it converges or diverges. Notice this is very similar in behavior to 1 over 2 to the nth power. So let's compare it to that one. Okay, so now what kind of series is this? This is a geometric series where what? Well, let's write it. How do you know it's a geometric series? Well, let's write it this way so it's clear. So this can be rewritten as what? Okay, so it's a geometric series. What's R? R is a half. Well, a half is less than 1. Right? So that means this is a convergent geometric series. Okay, now let's compare the nth term. Well, we look at 1 over 2 to the nth plus 1. Now, is this always less than or equal to that? And the answer is yes. So this is always less than 1 over 2 to the nth for all n greater than or equal to 1. That is true. Since this is always true, oh, by the way, also notice that this is positive and increasing on n, right? So, but since this is always true and this is convergent, we know that these partial sums are bounded. So the partial sums for this expression are bounded from above. And so therefore, we know by the comparison test that the series also converges, right? So hence I'll just write it this way. Converges by the comparison test. It's that easy, right? So you're just making sure that the conditions are satisfied, and then once the conditions are satisfied, then it's either going to diverge by the comparison test or it's going to converge by the comparison test. Okay, so again, just to recap, this is very similar to this. This is a convergent geometric series. Since this is always less than this, and this is a positive increasing terms, right? So we have a increasing sequence of partial sums. And since this series converges, its sequence of partial sums converges, right? So which means that the sequence of partial sums also converges because it's what? Bounded from above by this one. It's a positive increasing sequence of partial sums. So that means that the sequence of partial sums for this one has to be bounded. So since it's an increasing bounded sequence of partial sums, by the monotone convergence theorem, it is convergent, hence the series is convergent, and again, that's by the comparison test. So now, again, I'm saying all that, but in really all it comes down to is, hey, if I'm comparing these two, and this is a convergent series, and all of the nth terms behave where the nth term of this one is always less than this term for all n greater than or equal to some value, then by the comparison test, it's either going to converge or diverge, right, depending on the relationship. Okay, enough of that. Let's do the next one.